Hi, welcome to the webinar. This is about mesh and roaming. My name is Gabriel Reyes. I'm the sales engineer here at Ingenious. So I want to be sure that we leave ample time for questions because this is a very, very important topic to a lot of people, and that's why we started a little bit early. Okay, so first, let's do some housekeeping measures. Sorry about that. So first, we're going to talk about what the agenda is. We're going to go over some partner benefits. Then we're going to dive right into it and go mesh, roaming, and then we're going to leave ample time for the questions and answers. So you sign up to the partner program at partners@ingeniustech.com. I highly recommend it. We have access to all kinds of important information and benefits, such as special dealer prices, access to the Easy Wi-Fi planner, and also certification and training, such as access to this recorded webinar. You can find it at partners.ingeniustech.com. Okay, so without further ado, let's get started with mesh and roaming. So first thing I want to get started with mesh is that it's a very different technology than roaming. It's actually mutually exclusive than roaming. A lot of people think of it as the same, and I could see where they could get confused due to the, consumer space type of products out there. I would say mesh and roaming at this point are probably so much intertwined. It's almost intertwined as VLAN and subnet. As you know, VLAN is a different type of technology than actually subnet. So let's go into what roaming is. So first question I always get asked about mesh is, what is mesh? Well, the best definition that we could come up with mesh, or I could think of mesh, is network traffic path resiliency. Now, this is important for the phrasing of here, because it's talking about network traffic, not just about the link. Because I get a lot of times where people would asking, well, what's the difference between mesh and spanning tree and link aggregation or other type of technologies that offer link resiliency? One thing is they offer link resiliency, which is just specific to that one little area they're worried about, just that one link. Mesh is worried about the entire network as a whole. So that's the entire network traffic path. And that's the reason why I define it as network path resiliency as opposed to just link resiliency, as the other technologies are going to be. So, like I said before, there's certain technologies that we have, in the wild world that give us kind of similar behaviors of mesh, but don't quite give us mesh. For example, we have spanning tree. Now, when spanning tree first came out, it was actually used for actually controlling how traffic flows to the network. It's because at that time, devices were expensive, routers were really expensive, layer 3 added a lot of latency, and so it was a lot faster to do things at layer 2. And so that's where it first was doing. It had a lot of things, but that's what it was being used for primarily during that time. As time evolved and networks got better and equipment got faster, and layer 3 became more at wire speed, there's less need to actually do that type of traffic flow at layer 2. So now it's being used for loop prevention, but it's still being used in modern technology for that. Now, one thing to note about spanning tree is that it's not recommended to be putting on half duplex mediums. So that's kind of important because from previous webinars, as we described, wireless is a half duplex medium, which means you're only able to talk or listen, but you can't do both at the same time. And because of that, certain protocols that require a keep alive or some kind of feedback don't operate very well in wireless environments. And that's the reason why mesh is really good, because it actually is optimized for that particular type of medium. So with spanning tree, as it says in the slide, you get no load balancing or traffic aggregation, but you do get link resiliency. So the next technology that we have on a wired side that gives us a little bit, benefits of what mesh has is link aggregation. So link aggregation is majorly used for getting a lot of lower capacity links and aggregating them so they could be a higher capacity link. Now, the topology of a lag would be mostly like a point-to-point. Mesh is different because mesh actually has a lot of different points. So lag is mostly used for that, and if one link goes down, the other link will take over, so you kind of have link resiliency there, but also you have the benefit of having a load balance type of technology within the lag. And some other vendors do like round robin or weighted round robin for that, and that's mostly how you get into link aggregators, or load balancing. Link aggregation is exactly that. It just aggregates the link. Load balancing is actually splitting up the traffic amongst that, which mesh actually does that. It actually defines what the better path is, and per frame basis sends it across across that path based upon the metrics. So it behaves mostly like a routing protocol, but done at layer 2. And that's what the mesh topology does. So what's the benefit of mesh? Well, we do have two types of deployments for mesh. The one that mostly people are talking about is the indoor ones. For the indoor ones, most of the time, if you look at all the other vendors that do indoor mesh, the cutoff is around 6 to 10,000 square feet. So you're not going to be using it in a large enterprise space or for high capacity requirements for businesses. Mostly it'll be used for consumer grade for indoors. Now, it's a very different outdoors. Outdoors, it's mostly used for industrialized types of applications. The benefit of mesh for outdoors is that it's easier to deploy. Basically, there's no need to plan how the traffic's going to flow through the network. Basically, you just pop these up and it'll automatically find the best path for you. Now, that does have a downside as well, which we will talk about in the later slide. It also has built-in high availability and failover. So you heard of mesh having self-healing, methods of techniques. So if one link goes down, the traffic could be rerouted, and then when that link comes back up again, it'll reroute through that link if need be. So what are the disadvantages of mesh? Well, for one disadvantage is loss of traffic flow control. So as I stated earlier, where they automatically find the best path, sometimes the best path for the traffic may not be adapted for the traffic type. For example, we had a large deployment of security cameras in a condominium complex in Washington State, and they were using another vendor that was using mesh, and they were running into problems with their deployment. It was pretty large, and the problem was that the cameras were not able to send the flow of traffic to MVR within the appropriate time. And so they would have like cutoffs, they would have their PTZ cameras showing offline. They're having a lot of problems such as that nature. So what we did was we actually designed it to use our WDS so we could actually control the flow of traffic across those links so they would actually have better performance. So that's one way in which mesh even does have the advantage of you just plop it up and it'll find automatically the best path to go through and it'll use it, but doesn't necessarily mean the best path based upon whatever metric it has is going to be matching the application that's flowing in the network that you need for its metrics. One thing also, if you're going to be doing mesh, is that if you have a lot of links that are redundant, you're going to have to add more equipment, and that's going to add to the cost. And some of these things are not cheap for outdoors particularly, and so it may end up being a higher equipment cost with a lower performance in a mesh network as opposed to just something like a WDS bridge. One other thing about mesh is, or two other things about mesh, is that you're at the mercy of vendor proprietary protocols. A lot of people don't know this, but mesh, this is the third time mesh has been around in the wireless industry. And this is the time is actually sticking around in the marketplace, but mostly in the residential space. Mesh is actually standardized in 802.11s, but if you read through the standardization or any documents surrounding that, the reason why many vendors do not implement it as a standards base is because they want to keep the proprietary nature of it so they can maintain their profit margins. That's pretty much the long and short of it. So when you do a mesh, you're pretty much locked into a single vendor proprietary protocol, and you're stuck using those particular type of products. Now, whether the product or not is good for you for IP rating or for different types of antennas, indoors or outdoors or power draw, you're pretty much limiting yourself to the availability of mesh points or devices you could have on the network for either client access or performance. So let's talk about roaming now. So roaming is very different than mesh. It has nothing to do with traffic resiliency or path resiliency. Roaming is basically you want to have a wireless client transitioning from one AP to another, or to a frequency band to another frequency band, either another AP or the same AP. And you want it to be transparent to the application or user. So you are going to have a transition. There's no such thing as a zero handoff in a multi-channel architecture in wireless. So basically, you are going to have something called an FT, a fast transition. It is going to break quickly and then reassociate again. And you want to make sure that the breakage and reassociation doesn't exceed the time in which the traffic flow for whatever application you need is flowing through. So the metrics for, let's say, a real-time application like a Skype call is going to be much more stringent than something like an email server that you push and pull on one of those basis there. So that's the reason how an application in a roaming would behave differently. So, and one or the other. So we have different types of roaming. We have nomadic roaming. That's what we first started off with. in roaming. Then we have seamless roaming, which people expect now for roaming to be in the contemporary times. Then we have band roaming, which vendors call band steering. But when you go between the 2.4 and 5 gigahertz, that is considered a transition, so that is considered a roaming type of event. So one thing I want to talk about roaming is that it's very variable dependent. So there's a lot of different variables that go into roaming, and there's a lot of things that are gotchas in roaming that if you don't take into consideration, you will see some weird behaviors, and you may have trouble troubleshooting it unless you understand the components of roaming and why one roaming behavior is different than another roaming behavior. So for nomadic roaming, I call it island coverage. Basically, it's a user that only cares about Wi-Fi signal at point A and point B. It's mostly used in even modern clients for the roaming algorithms, such as laptops, which are, they're better clients. They have better antennas, bigger batteries. So they're expecting that particular device not to be seamless, but to be like a nomadic type of roamer. So depending upon the client count of your network, the roaming behavior is going to be different, particularly on different types of clients. So the laptops will have a different roaming behavior than a cell phone or a tablet, even though the access points are not going to change in the infrastructure. You have the same number of access points. Then we have seamless roaming. Oh, sorry. For the example for nomadic roaming would be, let's say I am in a conference room and I have a desk that's further away from the conference room. Well, I'm on my laptop and I want to be in the conference room working. And then I want to close the lid. The device goes to sleep mode. And then I want to go to my desk, open up my lid, and then continue working again. That would be an example of nomadic roaming because I don't care about the network performance between point A and point B, between the conference room and my desk. I only care about my desk, and I only care about the conference room. So that's why I consider island coverage. I only consider about islands, areas which I am only interested in having. Seamless roaming is different. I call it ocean coverage. That's when the user cares about Wi-Fi signal from point A and point B and everywhere in between for their application. And one example would be if I have a voice over Wi-Fi call, and I take it in the conference room, and I want to be able to walk to my desk. I want to be able to maintain that call as I go across those areas. That would be an example of seamless roaming. And band roaming, which would just be going between 2.4 and 5 gigahertz, which is important because some vendors do band steering, in which they have the same SSID, and they want to go from 2.4 or 5. They have band balancing or anything like that. It's important to know that when you're doing that, you are doing a roaming algorithm, a roaming type of behavior. And when you do that, you are adding to the roaming. So one thing about roaming is you don't want to do it too much, you don't want to do it too little. So if I do it too little, I'm sticking on to the lowest data rates. And particularly on the application, it may not survive in the lower data rates for nominal data rate. If I roam too much, what's going to happen is that I'm actually using more of my airtime looking around for people to roam to than actually pushing real data through. So that's why you have the Goldilocks of roaming. You don't want to do it too much, you don't want to do it too little. So let's start talking about designs for roaming and what they actually look like. So this is a real world example. We have a car dealership here. Backstory on this was that they had one access point, and that in the break room, that access point was just one covering the entire facility. Now they ran into problems. They had dropouts. They had, they weren't able to go out to the lot, and so they wanted to do more with their Wi-Fi, and that one access point was not covering it. So we designed a wireless network for them that was particular for their application, which was a VPN-based. Most of the time in car dealerships, they have a VPN-based application that runs on their tablet, and it doesn't really survive very well with long breakages. So going from one access point where they had almost no breakage, going to multiple access points where they have to break for the transition, we have to design it appropriately for seamless roaming for that particular type of client. So you can see we went from one access point to 7 access points in this particular type of design. So this was perfect for their cell phones and tablets for roaming, for maintaining connectivity for that application. But they also had laptops too. So they're looking for nomadic type of roaming design as well. So this is the same design, the same number of access points. It's just that this is a different SSID for those particular type of clients. So the coverage for this SSID for the laptops was be different than for the tablets and the cell phones. And so in this one, we went from 7 to 3. So in this case, the laptops did nomadic roaming. They wanted it in particular areas. They didn't care about it in the entire location. So that means we have only 3 access points. And that's very different than their guest access, which was just 2.4 gigahertz only, which we do just for coverage only. There's really no expectations of roaming in 2.4. The reason for that is because the newer roaming standards that came up was actually rolled up into 802.11ac, and 802.11ac was only for 5 gigahertz. So you would see better roaming behaviors on clients or access points, even on which band you're running on. So if I was on 2.4, there's no requirement for me to roll up those standards into 2.4, because the last time 2.4 was updated was 2009. So it's only required that I have up to 2009 standards for 2.4. Well, a lot has happened since 2.4, since 2019 in the wireless industry. So you would see that the roaming behavior on a particular client will actually behave differently, even if you operate in 2.4 and 5 gigahertz. The reason why this is important is because remember the band steering we talked about earlier? Well, if they force you to go from 5 gigahertz to 2.4 to 5, you'll even notice on the same client, the roaming behavior will be very different in a different band, depending if the client has support for those new roaming features or the access points, because it's optional and not mandatory in 2.4 to have the newer standards rolled up. So that's why I said that roaming is very variable dependent, because depending upon a lot of variables will determine the behavior of the roaming. Okay, so now we're going to be doing some questions and answers. Let me bring up the question again, sorry about that. So one question we have here is, will this webinar be recorded? Yes, it'll be recorded and it'll be available within our partner program. We could go back to the slide again if you need to on whether how to access the partner program. Sorry about that. So you can have access to this recorded webinar. Okay, we have another question. It says, can you please explain again why there is loss of traffic flow control? Sure. So when you do mesh, what it does is it does a roaming algorithm at layer 2. And when you have a roaming algorithm, you're not telling it which way to go. It's figuring out on its own which way to go. And because wireless is half duplex medium, and also there's an arbitration process involved with it, on a frame-by-frame basis, the metric will be different. So in 1 second, maybe that path that I took may be better than another path. Another second, it's actually less than a second. Another path will be better than the path that I had previously. And so in that way, I can't control the flow of traffic. So if I go one direction over another direction, the other direction I choose may have more hops. When I introduce more hops, it introduces more latency and bandwidth loss. And so that's the reason why if you can't control the flow of traffic, you cannot say, hey, this type of application is going to be qualified for this all the time, because it's going to be jumping around all the time. The same thing as like a packet switch network and a circuit switch network. Sure, so hopefully that answers that question. Next question we have is roaming questions. When roaming is when roaming is enabled, it appears that we are transitioning across APs. The connection seems to be established, but traffic will not flow for about 3+ minutes as a spanning tree is playing a role. Please advise. Not quite too sure if this is on our access points or other ones. That may be a support thing that we could address at a later time. But yeah, for most times with that with that particular roaming should be the best defense against a roaming is a good roaming design. In this case, it could be probably like an ARP timeout either on the client or the infrastructure that may be holding on too long and needs to time out, and then you see it somewhere else. Okay, so another question. Hopefully, it answers that, Donald. Another question is, do mesh standards automatically apply any sort of RTS CTS optimization, or is that something we need to do or tune ourselves? So RTS and CTS, sorry. So for RTS and CTS, mostly that's mainly used if you experience any kind of virtual carrier sense arbitration process in your network. I know if you do packet captures on Apple devices, they're kind of bad clients. They'll actually do CTS to self a lot to try to clear the air so that they could have full and uncontended access to the medium. And that's one complaint that we had about Apple. They kind of cleaned it up a little bit, but they still kind of do that. So when you do an RTS and CTS, you're adding an extra frame, an extra process of stopping in order to have access to the medium that actually decreases the efficiency of it. So will mesh have RTS and CTS? That's really up to the vendor proprietary protocol to even have that type of arbitration process in there. So some vendors may have it, some vendors may not do it, because there's no expectations of clients to be on there. So they may not have RTS and CTS on that. But that's a good question. Thank you for that. So the next question is, what's the lowest hardware AP that could do mesh? So that would be our EWS line. So I would say something like, let me see, our 550s could do it. That's the wall plate one. Our 360s, our 350s. So those particular models would be able to support mesh. Hopefully that answers that question. Okay, so it says, now they have another question to say, just to clarify, are you suggesting mesh is not for larger space environments? Well, that's kind of a good question there, and that would allude to that, but I'm saying mesh is not for larger space environments that have more constrained network traffic requirements or metrics. So you could have a larger environment, and so long as the traffic metrics don't exceed what the network could handle for the latencies that are being added for meshing or for the bandwidth reduction, then you should be fine. It's only to the point in which the application traffic exceeds the threshold of what the network can deliver, that's when you experience performance problems. And because there's no control in mesh of that, you have a higher statistical chance of having that occur in a large environment with a real-time application for the mesh, like I was describing. Cameras are pretty much real-time. You have to be going at a certain time. If they're dropped, they're dropped. There's no retransmission of that frame. So hopefully that answers that. So it says, another question we have is, why do iPhones and tablets have such a tough time staying connected on Wi-Fi while my ancient Android works fine? So that could be, it depends upon, I think, the infrastructure at that point and the type of protocols that are included in there. One thing to look at is like, what type of infrastructure do you have there? But most of the time when we like to, there's some best practices that you want it to be deployed. For example, let's say the Android. We know that the Android prefers 2.4 over 5 gigahertz. So let's say you have access points that are deployed and you have a higher gain on 2.4 and it actually is auto power. So let's say it has the highest output power 2.4. Well, according to the client, 2.4 looks better than 5 to connect to. And so I'm actually able to connect to 2.4 and have a higher signal to noise ratio there, and I will be staying on 2.4. Let's say clients are on 5 gigahertz, and let's say it was designed for 2.4, not for 5, and so 5 I have, I disconnect because I only have a certain basic data rate of 5. Let's say the application doesn't survive with data rates that low, and so I'll basically disconnect more on 5. So that could be the reason why, at this case, he's saying that your iPhones or tablets have a tough time staying connected on your Wi-Fi as your ancient Android phone works fine. The number one question I have is which band? One thing to figure out is, one thing in your troubleshooting is to figure out, is it a certain subset of clients? Is it all clients? And is it one band or is it all bands? So that's be something for troubleshooting. So one thing I'll troubleshoot is basically, in this case, you said you identify the subset of clients. I would say, is there any commonality within the clients, like a particular, operating system, or a particular, like, is it iPhone 4s only, iPhone 5s only, or is it only on a particular band? Is it only on 2.4? Is it on 5? That would be one way I would actually start to troubleshoot that with. Hopefully that answers that question. Sorry about that. Okay, so one question is 2.4 versus 5 typically requires having 2 SSIDs, one for each. Is there a way to have a single SSID that can utilize both frequencies and yet keep a single SID for a single use? Yes, Craig. That's what band steering was designed for. Now, one thing to take into consideration is your client capabilities. If your clients are only 2.4 and not 5, certain types of band steering will actually have negative results on the user experience as opposed to positive results. For example, if I had an iPhone 4 and I had band steering at 2.4 and 5, the logic of iOS is that if I get rejected from a particular SSID a particular number of times, I'll just give up. Sorry, is that still? I'll just give up. So in this particular case, band steering is going to ignore the 2.4 gigahertz, probe response, waiting for the 5 gigahertz. And if it doesn't get the 5 gigahertz, well, then it will respond back in 2.4. But it may exceed the number of tries the client has, and so the client would just give up on it. So in that particular case, yes, you have one SSID, you have clients, you want to band steer them, but because of the roaming algorithm of the client, that means that you're going to have negative behaviors on that. And that's what we've seen too with some iOSs. So hopefully that answers that question right there. The best thing to do is just do an offset between 2.4 and 5 of at least 6 dB. 8 to 9 to 10 better with more obstacles in the way. So another one says, another question is, what's the dealership the same 7 access points, but configurations that set up to behave in different specific way you showed? I'm not quite too sure about that. Yes, it was the exact same. The exact same 7 access points. They're all physically in the same location. It was just basically showing you the changes of which ones have 2.4 gigahertz enabled, which ones don't. They all have 5 gigahertz enabled, but of the 5 gigahertz, one SSID was dedicated towards a particular subset of clients, and the other SSID was dedicated to a particular different subset of clients. So in that particular one, you would actually have different coverage patterns for even different SSIDs on 5 gigahertz, and that's what I was trying to convey there. In which that if I want to do a seamless roaming design, it would look very different than a nomadic roaming design as opposed to just a coverage only in 2.4. So the whole point of that was in a design, we have different parameters to account for, and a design may have different sub-designs within that primary design. So I may have like 3 or 4 designs in one design. That's what that I was trying to allude to. Okay, these are all great questions. Another question is from Jack. It says, actually, that was, sorry about that. I don't know if that's pertaining to ours. So the answer to that is yes, you can upgrade your devices to a newer firmware, so long as it's supported, and you have access to all that on our website as well. They tell you which the newer firmware support and don't support. Okay, thank you for that question. Okay, so we have another question. It says, do you recommend creating a mesh in a normal office or retail indoor setting below 5,000 square feet using EasyMaster controller? You can using the EWS switch or controller. If you have the option of doing a hardwire connection, I would say do that first, and then mesh would be the last option that you would go to. Most of the time you see mesh in, particularly for a retail indoor space. I'm not really looking for mesh for that because of the type of traffic that flow there in office and retail. For consumer base, that's fine, but for office or retail, I would stick with hardwire. You get the best performance of that in that way. I would say for residential, you do mesh that way. Okay, so another question we have is, how does fast roaming work? Setting inside AAP. Okay, so I'll answer this question. Fast roaming is actually considered as a standard called 802.11r. So what that does is it adds an information element into the beacon. And that information element is supposed to be able to communicate to clients that they've been vouched for within the 802.1x environment. So let's say I have a Radius server, and I want to have an extra level of protection beyond the pre-shared key. I actually do a 802.1x authentication. So when I first walk into an 802.11r environment, the client will make an 802.1x authentication to the Radius server initially. So that's going to be the longest authentication that's being done, up to 700 milliseconds or 1,500 depending. As I go through the access points that are part of what they call a mobility domain, and they all have to have that particular information element in the SSID to identify themselves as such. That means that as I go through each access points, I will not have to do the initial 802.1x authentication. The access point will vouch for me so long as I stay in the mobility domain that I already made the initial 802.1x authentication, and that will just mean I do the 4-way handshake, and that'll be similar to pre-shared key authentication, and that dramatically reduces the authentication time. So that means the authentication time would be in the realm of 70 to 100 milliseconds as opposed to 700 to 1,500 milliseconds, which will greatly improve your roaming experience because certain applications don't survive if they break for a longer period of time. So hopefully that answers that question. Okay, so we have another question, SSID for ease of user use. SSIDs are going to be basically virtual network names. So according to the client, they'll look at an SSID as another physical access point, even though it could be the same physical access point, it's just a logical division. So hopefully that answers that question. Okay, so it says another question is, what's the min/max distance of mesh APs? Well, that all depends upon the environment, the protocol they're using, the antenna, and also if they have visibility to each other. I would say for Most of the time, it would be in the long range of different frequencies, probably about 1,000 to 2,000 feet for omnidirectional. You could get, I would suggest probably do it at lower because these are designed to be, having redundant links. And so if one long link goes down and there's no other hop to another long link because you exceeded the boundary of your association, that means that pretty much you defeated the whole purpose of mesh. So shorter runs will be better for mesh than longer runs. Okay, another question is, I use the EEP 1300. That's a great model that we have. There are a few locations with no Ethernet cables. So will the 1300 support in the next release? I'm assuming you're asking, will 1300 support mesh in the next release of the firmware update? We have plans for that, not in the next release, but further in the future for that particular model. I would suggest if you don't have any Ethernet runs there, you could always look into our backhaul solutions like the NStation 5 ACs or ENS 500 ACs, and then produce that wireless backhaul link there. Or you could go for our 360s or 350s that currently have the mesh built in on that. You could do that as well. And our 330s. Okay, so another question, is there any benefit to create a mesh type connection in site-to-site wireless links? Well, that's a good question. Now, I believe what you're trying to accomplish is you still want to have the traffic flow control of the links, as well as you want to have the link resiliency. In this particular case, I would say no for the mesh, as stated before, because point to point you have a longer run to do, and that mesh is pretty much not getting any benefit of mesh. You're actually getting hurtful of mesh of running the algorithm of something that shouldn't be run. I would say if you're looking for that, probably a better way of doing it, and what other vendors do as well, is you get a particular router that handles like OSPF or something with the link state, and that all travels back to a primary router, and that controls that actually controls the flow of traffic on the wired side, and that obviously goes across your wireless side. So you would actually have to introduce a particular routing protocol on the wired side for that to occur. Hopefully that answers that question. So it says, another question is, can we use mesh in a hotel with concrete walls and APs only on the middle floor, 3-story hotel? I would say for concrete, if you're using 5 gigahertz for the backhaul, it's going to be kind of challenging. That increases the number of density of access points. That may be more price prohibitive than actually running cable through to particular access points. I mean, it can be done, but then you're spending a certain amount of money and you're getting a certain performance of a network. You're probably better off spending money to run cable to get a better performing network than try to do it the mesh way in this particular case, since it's a high attenuated environment. And the particular types of application or flow of traffic you're going to be doing on a hotel environment. Okay, another question is, can you connect wireless devices to the back of the EMD1 that's connected via mesh? The answer to that is yes. For example, I need a VoIP phone. Now, for a VoIP phone, also take in consideration that, yes, you could. There is a one Ethernet port on the EMD1 you can connect to, hook up. Once you mesh it, you can hook it up to connect to another wired client. Now, you're talking about a VoIP application. So with a VoIP application, it's very important that you have consistent latency that's low. With mesh, like I said before, you cannot control the flow of traffic. So when you cannot control the flow of traffic, you cannot guarantee that particular latency will be there. Whether or not that's going to exceed or underwhelm the threshold of that particular latency that's required for the voice application, I would say you're putting yourself more at risk of having the application, have some hiccups than actually have a type of application that's smooth and seamless because of that particular the mesh algorithm thrown on top of that. So that's something to take into consideration when that particular application type or traffic flow type is going on there. But that's a great question. Thank you for that question. Okay, I have another question. It's the use of mesh degrades the bandwidth to each client, as it is using part of the band for communication between mesh points, where a roaming design has full-blown bandwidth capabilities. Well, roaming, as I said, is a different type of technology. You could have roaming with mesh. Most of the time people think of it as together, but roaming is also with access points that are hardwired too. So yes, you'll get the best performance of roaming with hardwire because hardwire is full duplex. It has no contention for the medium, such as wireless, and very rarely you're going to have any interfering sources on the wired side. And if they are, you could always overcome them by using fiber instead. And so for roaming, I would like to say, for larger applications or more mission critical applications, hardwiring the access points for roaming would be the best way to go. Okay, so there's another question here, and thank you for that question. Is what's the difference between seen in megabits per second for each one, mesh versus roaming? I would have to say you'd have to do nominal, not frame per frame, because as you can't control the flow of traffic, nominally as the traffic flows through the network, depending upon the environment, the protocol, it's going to change. So as you take a large data set of points, you could kind of get a median or an average of that, and you could say, okay, this is what on average you're going to be getting, or median you're going to be getting. When you control the flow of traffic, you're actually able to get able to control the data better of those data points. And so I would say the difference between each one on just one hop or one point to point would be in a low contained environment wouldn't be that much. I would say latency-wise, probably 1 to 2 milliseconds. For actual speed-wise, probably equates to maybe 1 to 10 megabits a second. But like I said, it depends upon the environment, because you're using a wireless unbounded medium for your backhaul that you still have to have contention to that particular medium. And so they still have to run particular arbitration processes. So you're still running the risk that you are going to trigger the arbitration process and throw in the random backoff timer, which we would explain R211 arbitration process in another webinar in the future. So those are all great questions, and we're kind of running a little bit on the time. So if you have any other questions, you can always email us. And it was great doing the webinar with you today. It's such great feedback, and hopefully you'll join us for the next webinar. Thank you very much.